All right, so we'll continue with the introduction in today's lecture. Hopefully, we'll wrap that up. So, the point where we had stopped last time was just beginning to talk about protocols. So, we have already seen what a computer network is used for. It's used to share information between distributed entities using some sort of communication mechanism. So, you have a node A which is sharing information with another node B using a network. Now, this network could be of any form. The internet is one particular example of a network. But all networks rely on protocols to manage any kinds of sharing of information. So these protocols operate at all the different layers that we spoke about last lecture. So for instance, the application layer has its own well-defined protocols like HTTP, DNS, voice over IP. All of these protocols, all of these applications have well-defined protocols. The transport layer has its own protocols, TCP, UDP. The routing has its own protocols. Now, the crucial thing about these protocols is these protocols define the format and order of messages that are exchanged between these entities. These protocols are not actual programs. Protocols just define the format of the messages that are sent and received and the actions that are taken once these messages are received or sent. So these protocols can be implemented either in software or hardware. So routers or Ethernet cards, they implement the routing protocols or the link layer protocols in hardware. Whereas application layer protocols like HTTP, they are often or almost always implemented in software. And again, as long as you follow the specifications of the protocol, you are under no constraint as to what programming language you use to implement it. So for instance, TCP or an HTTP browser on node A could be running, could be written in Java. The HTTP server it could be running in C. But both of them have to follow the specifications of HTTP. So as long as you follow the specification, it doesn't matter what language, whether it's software or hardware. So these protocols, these standards have to be carefully maintained in order for this communication or sharing of information to occur. So protocols are sort of the key ingredient of networks, and most of this course will be devoted towards studying of protocols and implementation of these protocols. Without these protocols, nothing would work. So we'll take a closer look at what these protocols are when we get into the application layer. But in most cases, these protocols are a set of request and response messages. So for instance, if you're browsing the web, the protocol would be a request sent from A of the form get index.html. This message gets sent across the network, and in return the correct response would be the HTML file, whatever the byte stream might be. So this is the request, this is the response. The response could also be if it's an invalid query. The point is that all requests have a well-defined response. The protocol should cover all cases. So that's the key to writing protocol, that you should cover all cases, and all cases are well-defined. And most protocols work in a request response kind of format, at least in the application layer. We'll see in the routing and transport layer that may not be the case. Now, this sharing of information, the sharing of information can occur in two different ways. The network offers two kinds of services, a connection oriented service and a connection-less service. So in a connection oriented service, the nodes A and B establish a well-defined connection channel over which all communications will occur. So connection oriented service and the other form is a connectionless service. So when you're browsing the web, when your browser is connecting to a web server, you're using the protocol HTTP, right? So does HTTP provide a connection-oriented service or a connection-less service? Connection-less? You're sure about that? Well, the answer to that is yes and no. I'm sorry? Well, HTTP 1.0 was connectionless. But HTTP 1.1 was connection oriented. Now the question is, when do you use connection oriented service, when do you use a connectionless service, what are the advantages of one or the other, and what applications should choose one over the other. Now from the web browsing example, HTTP had both forms of the service. What's the issue here? What does a connection oriented service mean, and what does a connectionless service mean, and when would a connection oriented service be better? Yeah.
Connection-oriented service provides reliability, and that you know that it will get there at some point.
That's not an essential characteristic of a connection-oriented service. Reliability is not a requirement of a connection-oriented service. Yeah.
The connection-oriented service will be faster once it's initially set up.
Yeah.
Because you don't have to maintain the handshake each time.
Right. So in a connection-oriented service, it's like making a telephone call. The first time you dial the number and a connection is established, then you're going to use that channel throughout your conversation, the channel or the connection that has been established. Whereas in a connection-less service, you'll have to dial every time you want to send or exchange any kind of information. So a connection-oriented service has the overhead of establishing the connection. So there's a handshaking protocol that goes on, which establishes this connection. Once the connection is established, you can exchange data over this channel. A connection-less service, on the other hand, there is no establishment of any kind of channel. Now, again, on the internet, this connection-oriented service is a very loose kind of definition. So this connection might happen at the application layer and at the transport layer, but at the network layer or the link layer, there is no notion of connection. We'll see what that really means. So the connection is at the upper layers. At the lower layers, again, the notion of connection breaks down. So what applications use connectionless service? An example of an application that uses connectionless service is a DNS query. When you're trying to resolve some host name, your typical transaction would be you just send in a query, you get the response back, and you're done with it, right? So suppose you are the client and here is the DNS server. In a connection-oriented example, you would send a message to the DNS server, which would be the handshaking message. The DNS server would respond with the handshaking. I'm not giving you the exact transaction that happened, but once this connection is established, then you send the query, and then you'll get a response back. And in a DNS example, once you get this first response back, you don't need this connection anymore. So you'll also spend time removing this connection. So establishment of this connection involves setting up of states at client and server. So the actual time you needed to get your response or what you wanted is only this. But because of this overhead of establishing the connection, you've almost doubled the time taken to resolve a query. And also there is this overhead of removing the connection. So for transactions which you don't expect will last a long time, there won't be a constant exchange of messages. Those kinds of services use a connection-less form of protocol. When we get to the transport layer, we'll see more details of how that is implemented, but typically connection-oriented services use TCP, whereas connection-less services use UDP as a protocol. Now that's not an absolute statement, because HTTP 1.0 and 1.1 both use TCP as the transport protocol. So in HTTP 1.0, for every sort of request and response a new TCP connection was initiated between client and server. Whereas HTTP 1.1 changed that to have persistent connection. So you establish a TCP connection, and then you can exchange a bunch of messages over that connection. And there is a timeout defined. So if you're silent for a certain period, then the connection is broken. Otherwise, that connection is maintained. Whereas in HTTP 1.0, for every request response, you have to establish a new connection. So again, in this example, this handshaking portion, this overhead is done only once in HTTP 1.1. You establish this connection, and then you get send query, get a response, send another query, get another response. Whereas with HTTP 1.0, for every query and every response, you needed a different connection. So suppose your web page had text plus 5 different images. In 1.0, it would need 6 different handshaking, 6 different connections, and that adds a lot of overhead. So those were the kinds of services that were offered by the network. Now let's take a look at what kind of entities live inside and outside the network. So these nodes which are communicating using a network, these are called end systems, or often they are called the network edge. So these are the nodes which are sort of the terminal points of the network. And typically on the internet, these nodes will implement all layers of the protocol stack. So you might tend to think that your desktop or your laptop or your PDA which is connected to the internet will not implement the routing layer or the network layer, but in fact it does implement the routing or the network layer. So a typical end system will have the app layer, it will have the transport layer, network layer, link layer, and the physical layer. So an end system or a node at the network edge implements all the protocol layers, whereas a typical node inside the network, which could be a router or a switch, will only implement network, link, so the network really has no idea of the application layer. It has no understanding of what HTTP does or what DNS does or what a typical P2P protocol is doing. Very little idea. Also, the network typically doesn't care whether the packet is TCP or UDP. All these protocol layers are implemented by having headers attached to packets, and the network layer does not look beyond the network does not look beyond the network layer. So even though the packets will have the transport and the app layer headers, nodes inside the network typically do not look at those headers. They typically do not process these headers. Again, I'm saying typically because there are some filtering rules, some firewalls. For security reasons, sometimes you do look inside the transport layer. To provide quality of service, sometimes you do look inside these layers. But in a typical definition of the network architecture, the end hosts implement all the layers. The network only implements network down. So in some sense, the network is dumb, and the end systems are smart. Now this architecture is very different from the architecture of the telephone network, the original voice network. In the voice network, the end systems are really dumb. The telephones don't do much. The telephone network, on the other hand, is the intelligence of the whole network. That's where all the protocols, all the switching mechanisms, everything is implemented. The end system is dumb. Whereas in this data communication or the internet model, the end systems which implement most of the complexity of the protocol stack. Now this is done mainly for scalability, and we'll see why this is important. So these protocol layers are kept as simple as possible and as minimal as possible to allow millions of flows to pass through this network. Now there are more ways to define these nodes which reside on the network edge or the end systems. One way to define them is by the client server model. So in the client server model, as sort of the name implies, one node is going to be the client for information, and another node will serve that information. So the web server is the server, and the browser is the client. This definition also implies that the server is typically a powerful machine. The client need not be, because the server is going to serve many different clients. So that's one view of what a client server architecture means. There's another sort of definition of the client server model, and that is defined by who initiates the conversation. So So who initiates the conversation in the client-server model? It's always the client. So a server typically sits listening for requests to come in. The request will arrive from a client. So in a client-server view of these end systems, the client is the node which is always going to initiate the communication, and the server will always respond. So in this initiator of communication view, the client is the one that initiates. Yeah. Okay. And the server responds. Yeah.
How about if you're in like an intranet or you have a finite number of nodes where the server broadcasts a message, like maybe the server broadcasts that it's going to be shutting down in 5 minutes or something? Then is the server initiating the conversation?
So in that model, the server is actually the client. So the server broadcasts this message. How does a typical node hear this message or listen to this message? Yeah. So listening on a port. So your client is sitting there waiting and listening on a certain port. So now in this communication, what you call the server has become the client, and what you view as the client has become the server, because your desktop was sitting there listening at a certain port for any communication which arrived from what you thought was the server, but in this model it becomes a client. So from that view, the initiator is always the client. So that's why there's a subtle difference between this server of information model and the initiating and responding to a communication model. Yeah.
You say when we're going to have some multicast channels, the client has to join. So you can say that the client has to join the channel before the initiator request. It's not always the case, but sometimes the multicast models you have to join the group to see the message.
In a multicast model, you have to join the group. Okay.
So in that case, since the client has to join first, he has to initiate the request to join the group.
Yeah.
And then when you broadcast the message, he will an answer to that.
So for the first part of the conversation, your listening node is the client.
If you have to join, you perhaps
Yeah.
the server to
Yeah.
join, so the client will want to meet the request, so then you will feed back to the client server model.
Right. So this client server model, this initiator communication model, is important when you're trying to actually code an application, a network application. So the client is always the node that has to initiate some sort of communication. So when you write that multicast application, it will operate in two different regimes. The first regime is when it has to join a group. So in that regime, that application will act as a client, and it will contact some multicast server that I want to join this group. Once that is established, then this application is sitting there listening, and then it becomes a server in this communication model. So when you're actually writing the code for this application, for the first part you have to treat this as a client, and it will have to do all the things that it needs to do to initiate communication. For the second part of the application, when it's sitting and listening, you have to code everything that it has to do to be a listener. So it has to keep some port open, keep some socket open for the incoming conversation. So in this model, your application can be both a client and server, depending on what it's doing. And clients and servers have well-defined roles and well-defined things to do. So this is very important from the programming point of view. The first information server and information requester is sort of the first cut look at what a client and what a server is. So that multicast group is an example. Another example is the second model is a peer-to-peer model. In a peer-to-peer model, the nodes don't have from the information provider and information requester point of view, the nodes don't fall into any category. So the nodes can both provide information as well as request information. So an example would be a VoIP phone. So VoIP phone, when you make the call, from this point of view, it becomes a client contacting a different phone, which for that conversation becomes a server. Once the connection is established, information is flowing both ways. So the role in terms of information providing is symmetric. Another example is a P2P client. Something like Kaza. So Kaza client, I've heard you can download files. So you can both download files and you can upload files using the same client. So in terms of information, it's symmetric. But the actual communications that happen, whether you're downloading files or whether someone else is downloading files from your server, then it can act as both a client or a server. So both functionalities are built in to this application, and this follows the peer-to-peer model. Now in this web servers will not be part of this peer-to-peer model, because a web server will rarely initiate a conversation and it will rarely accept information. I'm not talking about forms or uploading of information or queries of that sort, but a web server always operates in a server mode. So these are the two modes of operations of these end nodes. So that's what's happening at a very high level at the end nodes. What happens inside a network? So the network is also called the network core. This was the edge, the end systems, and the network itself is called the network core. Now, how is data transferred across this network? As we saw earlier, this network core consists of many different devices. At the network layer, all of them are routers or switches. So when two end systems are transmitting data across this network, how is this data being transferred? There are two models of this data transfer. One is circuit switching, and the second is packet switching. Now, it's sort of important to know the difference between the switching technology, which is circuit versus packet versus the data format. You can still have packets going on a circuit switch network. But the technology would be circuit switching. So what is circuit switching? Where is it used? Yeah. So telephone networks use circuit switches. So what's the characteristic of a circuit switch? Yeah.
You're designating a certain connection line in the network that you're held for this particular section. Right.
So in a circuit switched network, you reserve resources. In a packet switch network, no resources are reserved. Now, suppose you have a link which is 1 megabits per second. Let's say your network consists of only one such link. Let's say you have users that transmit at 100 kilobits per second. Let's say this is a voice call or a voice kind of connection between different nodes on the network. It could be anything actually, a web session or anything like that. So if you have circuit switching and your users, you know that they transmit when they're transmitting at 100 kilobits per second. To guarantee this 100 kilobits per second, how many users can you support? You can support 10 different users. So you can slice up this 1 megabits per second into 10 different slots. Yeah.
Can't you support more if you consider that the nodes will probably burst the information?
So that's the whole point of packet switching. So you're sort of going one step ahead. So if the users are transmitting at 100 kilobits per second, in a circuit switch network, each user has to be allocated 100 kilobits per second, a channel or a circuit on this link. So you can support 10 users. As soon as you have the 11th user, you don't have any available bandwidth left here because you have allocated that bandwidth to these 10 users. So you can support no more than 10 users. But these 10 users will be guaranteed 100 kilobits per second for the duration of the call, or for the duration of any data transfer that's going to happen. In a packet switch network, on the other hand, you don't reserve resources, and you take advantage of what's called statistical multiplexing. So now, additionally, if you know about these users, that they transmit at 100 kilobits per second, but they are active 10% of the time. So if you plot a typical user and the bandwidth that it's demanding, so this is 100 kilobits. So it will demand 100 kilobits for a while, then it will be silent, then again 100 kilobits for a while, and then it will be silent. So in a circuit switch model, this region where a particular user is silent, the bandwidth in this link that you have is going to be wasted. Right? You have guaranteed this bandwidth to this particular user, but this user is only active 10% of the time. So this is what you call a bursty user. It will demand or transmit information in these short bursts, will then be silent for a while, then again demand or transmit information in short bursts. So this could be a voice call where you're talking for some time, then you're silent. It could be a web browsing session where you download some web page, you read it, then you go on to the next link, then you read the web page, go on to the next link, and so on and so forth. So a lot of the communications that are happening over the network, they are bursty. Now if you know that this information transmission or transfer is going to be bursty, then what you can do is, instead of reserving resources, you let everybody in and you gamble on the fact that no more than 10 are going to be active at the same time. So if you have a collection of such users who are all transmitting at 100 kilobits per second and they're active 10% of the time, if you had 5 such users, can you support all of them over this link? Yes. I mean, even if all of them are active at the same time, you're only going to use 500 kilobits per second. If you had 10 such users, then again you can support all of them. Suppose you had 11 users, then in the circuit switch model you cannot support them until one connection is terminated or one call is terminated. But in the packet switch model, you're banking on the fact that 11 of them are not going to be active at any one point. So let's say, actually that's probably that can be given as a homework problem. If you have if you have 11 users What is the probability? All 11 are active. At the same time, if they are independent users.
I mean, it's not possible that they all be active because one of them can be supported.
So if one of them can be supported, then your network will have some problems. So what we are trying to get at is how often does the network get into those problems? So the users can be active. I mean, I'm on the call. I'll try to talk, and all of us can start talking at the same time. So we're just trying to establish how often does the network get into trouble. Now, if 11 users are using this network, the network will only get into trouble when all 11 of them are active. What if we had so let's say we take any time slot and 10% is the probability of any user being active. So the probability of being active is 0.1. So each user is looked at independently, and the probability of the user being active is 0.1. So what is the probability of 11 users being active? Yeah, it's going to be 0.1. Right?
You got a question?
What if you had 110 users? Would this probability increase or decrease? Increase. So what would the expression, how would the expression change? Times. Yeah, so it'll be 110, choose 11. We just need at least 11 of them to be active for the network to get into trouble. So roughly, as the number of users increases, the network will get into trouble more often. This is going to be an increasing function in terms of this number of users, fixing the probability. Now, the probability that greater than 10 are active if our number of users n is it's been worked out if n is 35 is about 0.004. So what does this imply? That implies that 99.996% of the time less than 10 or less than users are active. So the quality of service that these users see is going to be exactly the same as in a circuit switch network where you had reserved the resources 99.996% of the time. for a minuscule amount of time, the network will get into some problems, and we'll see what kinds of problems. So the packet switch network is able to support 3 times more users with really no perceptible drop in quality. If you're on a 1-minute call with this probability for 59.9 seconds, you'll observe no problems. For some amount of a time, you'll observe some kind of problems. But those problems can also be taken care of using buffering. So the circuit switch network uses the available resources kind of inefficiently. Packet switch networks use the resources much more efficiently. You are able to support a lot more users with almost the same quality of service. On the other hand, circuit switch will guarantee you the service for 100% of the time. So it gives a deterministic guarantee. Packet switch network will not give you that deterministic guarantee. So the model that is used in on the internet is packet switched. Telephone networks use circuit switched, but even telephone networks are shifting to the model of packet switched networks. For example, transatlantic telephone links, they transmit data using packet switched networks. Even your telephone calls are going using packet switched networks, not circuit switched networks, because they are just inherently more efficient. They have other problems that we'll look at later, but packet switched networks are much more efficient. Now, packet switched networks again there are 2 kinds of packet switched networks. One is a datagram network, and second is a virtual circuit. So in a datagram network, every packet that is going on that network is sort of sent or routed across the network independently. So a switch or a router here would look at every packet, look at the destination, and then send the packet along to the next hop. So in this model, this router, for instance, might send this packet along this path and the next packet along this path. Every packet is treated independently. The routing decisions might change over time due to various reasons, load balancing or other sorts of things. We'll get into the details when we look at the routing layer. Whereas in a virtual circuit network, once you establish a connection, then what you do is underneath this connection, a virtual circuit is established. And all packets going through this connection or through this between these 2 endpoints will follow the same virtual circuit. So the routing decisions in a virtual circuit network are made not on the basis of the destination of every packet, but it is based on the virtual circuit that this connection is using. So virtual circuit networks again have this overhead of establishing this virtual circuit. Whereas in a datagram network, packets just come and they're routed as they come and go. In a virtual circuit network, these virtual circuits are established, these packets follow the path. It doesn't mean that the resources are necessarily reserved, only that the path is established for the duration of the connection. And it has certain advantages. It can do faster switching. So the internet is a datagram network. Virtual circuit network, the examples are ATMs. ATM networks, you might have heard of them. They use virtual circuits. And also something called MPLS, which really sits on top of the internet. That also uses virtual circuits. So we'll take a detailed look at MPLS and ATMs and IP when we get to that. So this course will be focusing on packet switch networks, whether they are datagram or virtual circuit. An important metric of any network is the amount of delay a packet experiences going from one end to the other end. So delay and loss are sort of important characteristics of a network. So in our earlier example, if you're using that 1 megabits per second line with more than 10 users, then in those rare cases where the number of users increase beyond 10, some of the users would experience maybe delay or they'd experience loss. Data would get lost. So we'll see what are the various kinds of delays and loss models in the network. So let's first look at delay. There are 4 major kinds of delays that a packet can experience in a network. One is nodal processing delay. Then you have the transmission delay. You have propagation delay. And finally you have the queuing delay. So what's a nodal processing delay? The nodal processing delay involves the delay that is experienced by a packet while it's being processed at any of these nodes. For example, the router in a datagram network will look at the packet, will look at the destination, and then decide which link to send it out on. Yeah?
That means that for a virtual circuit network, it's probably going to be minimal nodal delay.
Yeah, for virtual, so that's where you gain in a virtual circuit network, because if you're thinking of a datagram network, and let's say you have IP addresses which are 32 bits, for each destination you'll have to do some sort of lookup, decide where it has to go, and send the packet along. So there are a huge number of possibilities, whereas you have a very limited number of virtual circuits. So the nodal processing delay is reduced if you're using virtual circuit network instead of a datagram network. So the nodal processing delay is, header processing and deciding where to send the packet along. Transmission delay and propagation delay, people often get confused. The transmission delay is the time taken to put a packet on the link. So what do I mean by that? Suppose your link has a capacity of R bits per second. Your packet is L bits. Then the transmission delay is going to be L times R. Yeah.
Is it ever possible that
L is greater than R? L is greater.
I mean, theoretically, yeah, there's nothing stopping.
so what would
Do in that case.
Well, then you just take more than a second to put the packet on the link. I mean, theoretically, there's no bound. The propagation delay, on the other hand, depends on the time it takes for the packet to move between two different nodes. So propagation delay is of the order of speed of light. And distance. So the further apart two nodes are, more is going to be the propagation delay. So it depends on what kind of medium you're using, whether it's fiber, whether it's air, copper wire, and the more the distance, more is going to be a propagation delay. So propagation delay between two nodes within a LAN is going to be minimal, whereas you'll still have a significant transmission delay or a queuing delay. Now again, transmission delay does not depend on the medium so much as what the capacity of that medium is. So for instance, we're all familiar with Wi-Fi networks. So you have heard of 802.11a, B and G, right? You've heard of B and G at least. So 802.11b can transmit at 11 megabits per second, whereas yeah. Yeah, sorry. It has to be L divided by R. It's in the units of seconds per second. So a B network transmits at 11 megabits per second, a G network transmits at 54 megabits per second. They are both using the same transmission medium, which is air. The speed increase is coming because of the way the different frequencies are being used by these different protocols. 11G in a sense uses more frequencies than 11B. So it's using the same medium. The propagation delay for the packets is going to be the same between two nodes, whether they are running 11B or 11G. But the transmission delay is going to be significantly higher for 11B, because 11B will just take more times to put all the bits onto the link. Queuing delay, on the other hand, is related to the capacity of the network or the capacity of the link. Suppose you're using a network. Okay, let's look at not a network but a bridge or a tunnel. If you're using, let's say, the GW bridge, depending on the time of the day, there is going to be some queue in this bridge or not. If you go late in the night, you'll just zip right through the bridge. If you're going during rush hour, you're likely to encounter some wait time here. Now the amount of waiting depends on the load level of the particular node. So over a period of a day, let's say 10,000 or 100,000 cars pass through this GW bridge. So if 100,000 cars are passing through the GW bridge, we know that the processing capacity of the fast lane or the cache counters there is at least 100,000 per day. Because if it was less than 100,000 per day, then those cars wouldn't be able to pass through. There'll be an infinite queue building up. So we know that it's at least 100,000 or more. So if the capacity of a node, for instance the GW bridge, is let's say A per second, and data is arriving at the rate, or data or cars, they are arriving at the rate L per second. Then the amount of queuing delay that you might encounter is dependent upon L over A. L over A is also called the load. Now, from the GW bridge example, we know that if we go during rush hour, we'll encounter a large queue. If we go late in the night, there's likely to be no queue. So when we are talking of queuing delays, we don't talk in terms of absolute quantities, but we talk more in terms of statistical measures, such as average delay or the variance in delay. So we always talk of average queue variance of the queue and metrics of that sort. So if we were to plot this average queue as a function of L over A, so this is 0, this is 1, then this average queue blows up like this. When the load is very low, the average queue that you encounter is going to be very small. When the load becomes close to 1, the processing capacity of the node, then the average queue that you see starts blowing up. Now this is assuming that all these packets or cars are arriving independently. This assumes what is called an open loop queuing model. Now there are models in which you can operate very close to capacity 1 and still have a low queuing delay. But those models or those networks require some sort of feedback. So TCP tries to do something like that. We'll take a look at this. An example for the GW bridge would be you listen to 1010 wins or one of the traffic reports. If you find out that there is congestion on the GW bridge, you might go take Lincoln Tunnel or Holland Tunnel. So by doing this kind of load balancing, you can operate close to capacity and not have a significant queuing delay. But you need feedback for that, some sort of feedback. In the absence of feedback, the queue grows like this. So these are the 4 different kinds of delays that a packet might encounter. So in today's high-speed networks, these 2 dominate. The routers in the core of the network process things really fast, and the queuing delay is also kept low by really over provisioning in the network. So the core of the network is typically operating at less than 30% of the capacity or less than 20% of the capacity. As soon as they observe that the arriving traffic is getting close to the 20% or 30%, they just increase the capacity of the link. So these days, typically, your queuing delay is quite low in core of the network. The processing delay is quite low. The main delay component comes from the propagation delay. On the other hand, if you get significant queuing, then you can also get losses, because these queues are stored in finite buffers. And if the queue grows beyond the buffer, then packets start getting dropped. So we'll continue from this point in the next lecture. The course TAs have been assigned and they'll take over the web page. The bulletin board has been set up. So just check the web page tomorrow and everything should be there. Yeah.
Do we need a CS account?
You need a CS account for that. Yeah. For the assignments you will need.